Before you open the bottle, before the hiss of carbonation, before the first cold sip touches your tongue, an industrial system has already been working non-stop. Every single day, billions of soft drinks are consumed around the world. Different cities, different cultures, different climates, yet the taste remains almost perfectly identical. This is not luck. This is industrial precision at its highest level. Before we go deeper inside these massive factories, make sure to subscribe and turn on notifications. Because once you see how this system works, you'll never look at a soft drink the same way again. Soft drinks are not made like ordinary beverages. They are not mixed casually. They are not produced slowly. They are not adjusted by taste alone. They are engineered. At an industrial scale, soft drink production is a balance between chemistry, automation, speed, and absolute control. Factories do not ask, "Does this taste good?" They ask, "Will this taste the same everywhere, every time, millions of times a day?" That single question defines everything. Modern soft drink factories operate 24 hours a day. No breaks, no weekends. No seasons. Machines replace human rhythm. Algorithms replace instinct, because demand never sleeps. In 1 hour, a single production line can fill more bottles than a small town will drink in a year. In 1 day, enough soft drinks are produced to supply entire countries. And yet mistakes are not allowed. This is the paradox of scale. The larger the operation, the smaller the margin for error. Soft drink factories are built like fortresses of precision. Water treatment systems rival those used in pharmaceutical plants. Quality control systems rival aerospace manufacturing. Logistics networks rival global shipping companies. All for something most people finish in minutes. The journey begins long before production lines start moving. It begins with raw materials sourced from across continents. Water, sweeteners, flavor compounds, carbon dioxide. Each one must meet exact specifications. Not close enough, exact. If one variable changes even slightly, the entire system responds. Adjustments are made automatically. Lines slow down or stop. Batches are isolated. Because at this scale, small errors become massive failures. And failure is expensive. A single recall can cost millions of dollars. Damage trust built over decades. Disrupt global supply chains. That is why prevention is everything. Soft drink factories are not designed to fix problems. They are designed to prevent them from ever existing. As we move forward, we will break this system apart piece by piece. From raw materials and ingredient control, to syrup creation and carbonation, to high-speed filling, inspection, and global logistics. You will see how chemistry becomes automation, how automation becomes speed, and how speed becomes global consistency. Because what you're about to see is not just how soft drinks are made. It's how modern mass production works. In the next segment, we enter the very first layer of this system, where everything begins and nothing is left to chance. Every soft drink begins with something deceptively simple: water. But inside an industrial soft drink factory, water is never just water. It is engineered. More than 90% of a soft drink is water. That is why water engineering is the true foundation of soft drink production. Before a single bottle is filled, before sweetness or flavor is added, water must be transformed. Incoming water arrives from municipal supplies, wells, or dedicated sources. But it never enters production directly. Instead, it enters a controlled purification system designed to eliminate uncertainty. First, mechanical filtration removes sand, rust, and particles invisible to the eye. Then activated carbon filters strip organic compounds, chlorine residues, and unwanted odors. What follows is reverse osmosis. This stage removes nearly everything: minerals, salts, and microscopic contaminants. What remains is almost chemically neutral water. Pure but unusable. Why? Because pure water tastes flat. And flat water ruins flavor. So minerals are reintroduced, not randomly, but with surgical precision. Calcium, magnesium, and sodium levels are adjusted to exact specifications. Sensors measure conductivity and mineral balance continuously. Every liter must match the reference profile. If it doesn't, the system corrects it instantly. If correction fails, production stops, no exceptions. This is how a soft drink tastes the same, whether it's produced in North America, Europe, or Southeast Asia. Not because the recipe is shared, but because the water behaves identically everywhere. Next comes sweeteners. Depending on region and regulation, factories use refined sugar or high fructose corn syrup. But industrial sweeteners are not judged by taste alone. They are judged by purity, density, and flow behavior. Sweeteners arrive in bulk tankers, stored in temperature-controlled silos to prevent crystallization or chemical breakdown. Flow meters measure viscosity in real time. Density sensors ensure concentration remains stable. If a sweetener thickens slightly due to temperature changes, the system compensates automatically. At this scale, sweetness is mathematics, not int. Then comes carbon dioxide. Co. is not added casually. It is treated as a structural ingredient, stored under high pressure, purified, and dried. Moisture in CO can destabilize carbonation and reduce shelf life. That risk is unacceptable. Pressure sensors monitor storage tanks constantly. Even slight fluctuations trigger alerts. Because carbonation affects more than bubbles. It affects mouthfeel aroma release, and how flavor hits the palate. Finally, flavor compounds enter the equation. These are the most protected ingredients in the entire factory. They arrive sealed, documented, and tracked digitally. Transferred through closed-loop systems, never exposed to open air. Never handled manually. Even quantities are calculated automatically. No human adjusts flavor ratios by hand. Because at this scale, trust belongs to data, not instinct. Before production begins, every ingredient is tested. Chemical analysis verifies composition. Microbiological tests ensure safety. Automated systems cross-check results against global standards. If one ingredient fails, everything waits. Not slows down, waits. This stage is slow, quiet, controlled, and deliberately cautious, because once ingredients move forward, speed will take over. And speed forgives nothing. With water engineered and ingredients locked into specification, the factory is ready for transformation. In the next segment, raw inputs become something new. Not a drink yet, but the concentrated heart of every soft drink. This is the moment where ingredients stop being separate and begin to become a system. After water is engineered and ingredients are approved, the factory enters one of its most restricted zones. The syrup creation area. This is where identity is formed. Not branding, not packaging. Flavor, identity. Inside this area, human presence is minimal. Not because people are unnecessary, but because consistency demands precision beyond human ability. Every process here is automated, monitored, and logged. Because a single batch of syrup will eventually become millions of bottles. The process begins with controlled water injection into massive stainless steel tanks. These tanks are not simple containers. They are regulated environments. Temperature is stabilized to fractions of a degree. Pressure is monitored continuously. Internal surfaces are engineered to prevent residue and contamination. Before mixing begins, the system runs a full diagnostic. Valves, sensors, flow meters. If one component fails the check, the system refuses to start. No shortcuts. Sweeteners enter next. Not poured, injected. Flow rate is calculated in real time based on temperature, density, and batch size. Viscosity sensors track how the liquid moves. If the sweetener flows too slowly, concentration increases. Too fast, and dilution occurs. The system adjusts automatically within milliseconds. This is not mixing by volume. It is mixing by behavior. Then comes the most critical step: flavor integration. The flavor concentrate is transferred through sealed pipelines directly into the mixing tank. No exposure, no human handling. Even technicians cannot see it. The amount added is determined by algorithms using reference profiles developed over years of testing. This is where flavor becomes mathematics. A deviation measured in grams at this scale can change millions of bottles. Once all components are inside the tank, high-precision agitators activate. Mixing is carefully controlled. Too aggressive and volatile compounds degrade. Too gentle and uniformity fails. Sensors monitor density, acidity, and optical clarity. Data is compared against global reference standards. If values drift outside tolerance, the system reacts. Sometimes by adjusting mixing speed, sometimes by altering temperature, sometimes by halting production entirely. Because flawed syrup cannot be corrected later. Once mixing is complete, the liquid is no longer water with additives. It is soft drink syrup. Highly concentrated, not consumable. Extremely valuable. This syrup defines everything that follows. Before approval, automated sampling systems extract microsamples. These samples are analyzed in on-site laboratories. Chemical composition is verified. Stability is tested. Sensory evaluation confirms alignment with the reference profile. Taste testing here is not subjective. It is comparative. The question is not, does this taste good? It is, does this taste identical to the standard? If the syrup passes, it receives digital approval. If it fails, it is isolated and destroyed. No reprocessing, no adjustments. At this scale, compromise creates risk. Approved syrup is transferred to secure holding tanks. Temperature controlled, sealed. Monitored, it waits there, stable and protected. Because the next phase will be the fastest and most aggressive in the entire factory. With syrup approved and secured, the system prepares to move at full speed. In the next segment, chemistry meets motion. A syrup is diluted, carbonated, and sent into high-speed filling lines. This is where speed takes control. Once syrup is approved, waiting ends. From this point forward, everything accelerates. Because dilution and carbonation cannot pause, they must flow. The syrup is transferred from secure holding tanks into blending units positioned directly before the filling lines. Here, precision and speed collide. The goal is simple but unforgiving. Dilute the syrup with engineered water and infuse carbon dioxide without altering flavor, stability, or mouthfeel. Blending happens continuously, not in batches. Continuous systems reduce variation, they allow real-time correction, and they eliminate downtime. Water and syrup meet inside dynamic mixers. Flow rates are calculated to the millisecond. Sensors track concentration, temperature, and pressure instantly. If water temperature shifts by even half a degree, flow ratios adjust automatically. Because temperature affects solubility, and solubility affects taste. Now comes carbonation. This is not bubbling. This is gas liquid engineering. Carbon dioxide dissolves best at low temperature and high pressure. So the blended liquid is chilled rapidly, often just above freezing. Heat exchangers strip thermal energy in seconds. The colder the liquid, the more it can absorb. Carbon dioxide is injected under controlled pressure. Not all at once. Gradual infusion prevents foam formation. Foam is waste. Foam is instability. Foam slows production. Carbonation levels are not chosen arbitrarily. They are defined by region, container type, and shelf life requirements. Glass bottles behave differently from cans. PET bottles behave differently from glass. Altitude changes pressure behavior. Temperature changes gas retention. The system compensates automatically. Sensors verify dissolved levels continuously. If carbonation drops, pressure increases. If carbonation exceeds tolerance, gas flow is reduced. This happens without stopping the line, because stopping would destabilize everything. Once carbonated, the liquid becomes fragile. Agitation causes gas loss. Temperature increases cause foaming. So, movement is controlled. Pipelines are short, curves are smooth. Vibrations are minimized. The liquid must reach the filler intact. Timing is critical. The delay between carbonation and filling is measured in seconds. If the delay increases, quality degrades. That is why carbonation units sit as close as possible to filling machines. In some factories, they are integrated into a single system. As the liquid approaches the filler, pressure is balanced. Bottle and liquid pressures must match. If they don't, carbonation escapes violently, which means foam, which means rejected bottles. Everything here is synchronized. Valves open and close in perfect rhythm. Pressure waves are predicted and dampened. Software models simulate behavior in real time. Because at this speed, reaction time matters. Once conditions are perfect, the liquid is ready. Not to wait, but to be captured. In the next segment, we enter the most visually intense stage of production, where thousands of bottles per minute are filled, sealed, and launched down the line. One mistake here can destroy millions of units. This is the point of no return. Once the carbonated liquid reaches the filling line, there is no pause button. Everything must move forward at speed. Modern soft drink filling lines are among the fastest production systems on Earth. Some lines fill and seal over 2,000 containers per minute. That's more than 30 bottles every second. And every single one must be perfect. Empty containers arrive first. Bottles or cans are delivered in massive quantities, stacked, compressed, and silent. They are unloaded automatically and fed into the line. Before filling, each container is inspected. High-speed cameras scan for cracks, deformities, or contamination. Air jets remove dust or microscopic debris. Anything suspicious is rejected instantly. No container enters filling unless it is flawless. Then comes pressure synchronization. Carbonated liquid cannot be poured like water. If the pressure inside the container does not match the pressure of the liquid, carbonation will escape. Violently dot so containers are pressurized with carbon dioxide before filling begins. This creates equilibrium. Liquid enters smoothly. Gas stays dissolved. No foam, no waste. Filling valves open and close in milliseconds. Each valve is calibrated individually. Flow rate, temperature, and pressure are controlled simultaneously. The system does not guess fill level. It measures mass. Every container must receive the exact amount of liquid, not more, not less. Overfill wastes product. Underfill violates regulations. Both are unacceptable. Once filled, containers move immediately to sealing. For bottles, caps are applied with precise torque. Too loose, and carbonation leaks. Too tight, and containers deform or crack. Torque sensors verify every cap. For cans, lids are placed and sealed through high-pressure crimping. Seam integrity is measured in real time. Microscopic leaks are detected instantly. At this speed, humans cannot intervene. Machines make decisions faster than operators can react. If a problem appears, the system isolates affected containers automatically. The rest of the line continues uninterrupted. Because stopping the line causes pressure instability, and instability causes losses. Noise fills the hall. Metal, motion. Compressed air, yet everything is synchronized. Every movement timed, every vibration dampened. This is controlled chaos. Temperature control remains critical. Warm liquid foams. Cold liquid behaves, so the environment around the filler is climate controlled. Humidity is managed to prevent condensation. Condensation causes slipping. Slipping causes misalignment. Misalignment causes failure. Once sealed, containers are no longer fragile liquid systems. They become transportable units, but they are not trusted yet. Because sealing does not mean approved. In the next segment, filled containers face judgment. Every bottle, every can. They will be inspected, tested, and verified at speeds faster than human vision. At this stage, the soft drink looks finished, but appearance means nothing. Once bottles and cans leave the filling line, they enter the most unforgiving area in the factory. Quality control. Here, perfection is not expected. It is enforced. High-speed inspection systems line both sides of the conveyor. Cameras capture images faster than the human eye can process. Every container is scanned. Fill level, cap alignment, label position, seal, integrity. Nothing passes unnoticed. Laser sensors measure liquid height to fractions of a millimeter. X-ray systems analyze internal pressure. Infrared sensors detect microleaks invisible from the outside. If a container deviates even slightly, it is flagged, rejected, removed. Without hesitation, the conveyor never stops. Rejected containers are pushed off the line automatically. No alarms, no drama. Efficiency demands silence. Random sampling happens continuously. At predetermined intervals, robotic arms remove bottles from the line. These samples are sent to on-site laboratories. There, technicians perform deeper analysis. Carbonation stability tests simulate weeks of storage in minutes. Chemical composition is verified against reference standards. Acidity, sweetness, and dissolved gas levels are measured precisely. Even color consistency is checked under controlled lighting. Because visual expectation matters, taste testing still exists. But not as you might imagine. No casual sipping, no personal preference. Trained panels compare samples to reference profiles. The question is not whether the drink tastes good. The question is whether it tastes identical. Environmental monitoring never stops. Air quality sensors detect contamination risks. Temperature and humidity are controlled to prevent condensation or microbial growth. In critical zones, clean room protocols apply. Because contamination doesn't always come from ingredients. Sometimes, it comes from the air itself. Every inspection generates data, and that data is stored. Every bottle is traceable. If an issue is discovered later, the factory can identify the exact production line. The time of filling the syrup, batch, the ingredient sources, nothing is anonymous. This traceability is not optional, it is a requirement. At this scale, accountability protects the entire system. Despite all this control, rejection is expected. Factories plan for failure. A small percentage of loss is built into operations. Not as waste, but as insurance. Because releasing a flawed product costs far more than destroying it. Only after passing every inspection stage does a container receive digital approval. Not from a human dot, from data. Approved containers move forward immediately. Because quality control is not the end, it is the gate. In the next segment, approved soft drinks leave the production floor and enter the global movement system, where speed, distance, and demand collide. Once a soft drink passes inspection, it enters a different kind of system. Not production. Movement. Approved bottles and cans flow into automated packaging zones. Robotic arms group containers with machine-level precision. 6-packs. 12 packs. Cases. Each configuration is optimized for transport efficiency. Nothing is chosen randomly. Shrink-wrap machines apply plastic film and heat it instantly. The film tightens perfectly secure but flexible. 4 glass bottles, reinforced cardboard trays are assembled automatically. Cans are stacked into interlocking patterns that maximize stability. Every packaging format is tested long before production begins. Packaging is not about aesthetics, it is about survival. Products must endure vibration, compression, and temperature changes. Simulations replicate thousands of kilometers of transport. Drop tests mimic handling accidents. Compression tests simulate warehouse stacking. Thermal tests prepare products for desserts, winter climates, and humidity. Only packaging that survives these tests enters the system. Palletizing happens at industrial speed. Robots stack cartons into precise formations. Weight distribution is calculated to the millimeter. One imbalance can cause collapse during shipping. Pallets are wrapped, labeled, and digitally registered. A barcode connects each pallet to a database that already knows its destination before it even leaves the building. From here, logistics takes over. Factories operate as nodes in a global network. Some pallets move to local distribution centers. Others go directly to ports, rail terminals, or cross-border hubs. Routing is calculated using real-time demand forecasts. The system does not guess demand. It predicts it, whether data influences shipping volume. Heat waves increase soft drink consumption. Holidays shift distribution priorities. Events, festivals, and sporting seasons trigger automated allocation changes. The factory responds before shelves are empty. Cold chain management becomes critical in certain regions. Temperature sensors travel with shipments. If limits are exceeded, alerts are triggered instantly. A delayed truck, a broken cooling unit, a container exposed to long at a port, the system knows and reacts. Distribution centers act as filters. High-demand areas pull inventory faster. Low-demand zones slow intake to prevent overstock. Products nearing expiration are redirected or removed. Nothing sits without purpose. Returns and damaged shipments are analyzed. Patterns are identified. Packaging is redesigned. Routes are adjusted. Every failure improves the system. By the time a soft drink reaches a store shelf, it has traveled through chemistry, automation, inspection, and logistics. But the system is not finished. Because the final stage happens outside the factory, in the real world. In the next segment, we step back and look at the entire system and why global consistency is one of the hardest problems in mass production. At this point, the soft drink has left the factory. But the system has not let go. Once bottles reach store shelves, vending machines, and refrigerators around the world, control becomes indirect but never disappears. Because consistency does not end at production, it must survive reality. Global soft drink companies face a problem few industries ever solve. How do you deliver the same experience to billions of people in different climates, cultures, and economic conditions? The answer is not marketing. It is systems. Production standards are global. But distribution environments are not. A bottle in Northern Europe sits in cold storage. A bottle in Southeast Asia faces heat and humidity. Carbonation behaves differently. Sweetness perception changes. Shelf life shortens, so the system adapts without changing identity. Regional adjustments are calculated, not improvised. Carbonation levels are slightly modified. Packaging materials are adjusted. Storage recommendations are optimized. Yet the flavor profile remains locked. The consumer never notices. Pricing is also engineered. Manufacturing costs, logistics distance, local regulations, and currency fluctuations are modeled constantly. Factories adjust output volumes accordingly. Overproduction wastes money. Underproduction loses market presence. The balance is mathematical. Marketing campaigns feed into production planning. Advertising increases demand before it becomes visible. Factories scale output in anticipation, not reaction, because reacting is already too late. Retail feedback loops never stop. Sales data flows back into central systems in real time. Which products move fastest? Which sizes perform best? Which regions slow down? Production schedules adapt automatically. Even consumer behavior is studied indirectly. Consumption patterns reveal preferences. Time of day, seasonality, temperature. Factories adjust supply to match habits people don't even realize they have. Yet, despite all this control, unpredictability remains. Transportation delays, political disruptions, natural disasters. The system prepares for disruption. Redundant factories exist across continents. Multiple suppliers provide the same ingredients. Logistics routes are diversified. Because resilience matters as much as efficiency. This is why shortages rarely last. When one node fails, another compensates. Invisible to the consumer. At this scale, the soft drink is no longer a product. It is a global service, delivered consistently, continuously, relentlessly, and most people never think about it. They open a bottle, they drink, they move on. But behind that simplicity lies one of the most sophisticated industrial systems ever built. A system that does not sleep, does not pause, does not forget. In the next segment, we confront the cost of this perfection, the environmental pressure, energy demand, and future challenges facing industrial soft drink production. Industrial power is never built overnight. Behind every economic giant, there is a machine quiet, complex, and relentlessly efficient. By the early 20th century, industrial dominance had shifted from individual inventors to systems. Factories were no longer just places of production. They became engines of geopolitical influence. Nations that mastered industrial systems didn't just produce goods, they controlled supply chains, dictated prices, and shaped the future of global labor. The key transformation began with standardization. Before standardization, production was slow, expensive, and inconsistent. But once interchangeable parts became the norm, industries unlocked a terrifying level of efficiency. A rifle made in Detroit could be repaired with parts from Chicago. A machine built in Germany could be replicated in Japan. This wasn't just manufacturing progress, it was scalable power. Then came automation. Assembly lines reduced human skill requirements while massively increasing output. Workers no longer needed to understand the whole process, only their tiny role within it. Productivity skyrocketed, but so did dependency. Nations that owned machines gained leverage over those that only supplied labor. This shift quietly restructured the global hierarchy. Industrial leaders exported finished goods. Developing regions exported raw materials and cheap labor. The gap widened not because of talent, but because of capital access and industrial infrastructure. Once a country fell behind in industrial capacity, catching up became exponentially harder. But machines alone weren't enough. True industrial dominance required energy control. Coal powered the first empires. Oil fueled the second wave. Whoever controlled energy sources controlled factories, transportation, and eventually warfare. This is why industrial strategy was never separate from foreign policy. Pipelines, shipping lanes, and refineries became strategic assets, often protected more aggressively than borders. By mid-century, industrial insight evolved into something darker: industrial militarization. Factories that once produced cars could be converted overnight to produce tanks. Steel plants became weapon suppliers. Chemical industries fed both agriculture and warfare. Industrial flexibility became a national security asset. And this is where the real insight emerges. Industrial dominance is not about production volume, it's about conversion speed. How fast can an economy shift from peace to crisis? From consumer goods to survival mode? Nations that mastered this flexibility survived global shocks. Those that didn't collapsed under pressure. Then globalization rewired everything. Corporations replaced countries as industrial architects. Production scattered across continents. Efficiency increased, but resilience weakened. A disruption in one region could paralyze the entire system. Suddenly, the same industrial optimization that created wealth became a vulnerability. This realization is reshaping the world again. Today, industrial insight is no longer about cheaper labor. It's about strategic independence. Semiconductor, plants, battery factories, rare earth processing, these are the new pillars of power. Governments are pouring billions not to maximize profit, but to minimize dependence. Because in the modern era, whoever controls critical industries controls the future. And the next transformation will not be driven by machines alone, but by intelligence itself. The world is no longer divided by ideology alone. Today, it is divided by industry. What we are witnessing now is not a traditional war, but a new industrial Cold War. There are no tanks crossing borders, no bombs falling on cities. Instead, battles are fought through factories, patents, supply chains, and invisible digital infrastructure. At the center of this conflict lies one question: who controls the critical industries of the future? Without them, modern economies simply stop. Cars cannot be built. Missiles cannot be guided. Artificial intelligence cannot function. Entire nations depend on a handful of ultra-advanced fabrication plants, most of them concentrated in just a few locations on Earth. This concentration is not an accident. It is the result of decades of strategic industrial planning. Countries that failed to invest early now face a brutal reality. Rebuilding advanced industry is not just expensive, it may be too late. The expertise, ecosystems, and intellectual capital cannot be copied overnight. This has triggered a global scramble. Governments are offering massive subsidies, rewriting trade policies, and redefining national security around manufacturing. Factories are no longer seen as economic assets alone but as strategic weapons. And this time, the battlefield is everywhere. Trade restrictions replace tariffs, technology bans replace blockades. Talent migration replaces troop movement. The most powerful industrial weapons today don't explode, they disconnect. Cut a country off from advanced chips, and its military modernization slows. Block access to critical machinery, and its entire tech sector stagnates. Control key logistics, routes, and economies suffocate quietly. This is industrial warfare without gunfire. Corporations have become frontline actors. Once neutral entities, global companies are now forced to choose sides. Where they build factories, where they store data, and which markets they serve. All of it carries geopolitical consequences. Profit is no longer the only metric. Alignment matters. Meanwhile, automation and AI are accelerating the divide. Nations with advanced industrial ecosystems are entering an era of exponential productivity. Labor costs shrink, output multiplies. Decision-making speeds up. Meanwhile, countries stuck in old industrial models fall further behind, trapped between rising costs and shrinking relevance. This is not just an economic gap. It is a power gap. History teaches us a brutal lesson. Every major shift in industrial power eventually reshapes the global order. The steam engine birthed empires. Electricity transformed warfare. Oil decided the outcome of world wars. Now, data, automation, and advanced manufacturing are rewriting the rules again. The most dangerous part, this industrial Cold War has no clear endpoint. There is no peace treaty for supply chain dominance. No surrender for technological leadership. Only constant pressure to innovate or be replaced. And as nations race to secure their industrial future, one truth becomes unavoidable. The next global superpower will not be defined by territory, but by industrial intelligence, resilience, and control. The factories of tomorrow will decide the politics of tomorrow. The supply chains of today will decide who leads and who follows. This is not the end of industrial history. It is the beginning of its most decisive chapter. Every day, billions of people consume the products of industrial systems they never see. The machines keep running. The factories never sleep. The supply chains stretch silently across oceans and borders. And most of the time, we don't notice them. But behind every bottle, every device, every everyday convenience, there is a hidden world of precision, power, and control. A world where milliseconds matter, where microscopic flaws can shut down billion-dollar operations, and where decisions made in control rooms ripple across entire economies. Industry is no longer just about production, it is about influence. It determines which nations rise, which fall, and which remain dependent. It decides where jobs move, where wealth accumulates, and where innovation flows next. The factory floor has become one of the most strategic spaces on Earth. What you've seen in this series is not just how things are made, it is how power is built. From raw materials to automated lines, from quality control to global logistics, from industrial secrets to geopolitical leverage, these systems quietly shape the world we live in, long before politics reacts, and long before headlines catch up. And as technology accelerates, the gap widens. Factories grow smarter. Machines grow autonomous. Decisions shift from human judgment to algorithmic precision. The future will not belong to the loudest voices, but to those who control the systems beneath the noise. This is why understanding industry matters. Because the next revolution won't start with protests or speeches. It will start with a breakthrough in manufacturing, a supply chain redesign, a factory that outperforms all others. The real question is no longer what we produce, but who controls how it is produced. And now that you've seen behind the curtain, you'll never look at everyday products the same way again. If you want to understand the hidden forces shaping the modern world, from factories and machines to power, profit, and geopolitics, subscribe to Industrial Insight. Like this video to support deep industrial documentaries. Comment which industry we should expose next, because the future isn't decided in public. It's decided in places like this. Industrial Insight, where the world is built.